This video is for Chemistry in the Earth System, Unit 1.4, Earth's Interior. Today's essential question is, how do physical conditions and mineral composition change with depth beneath Earth's surface? Hello, baby birds! Let's begin this video with a place you might know, Yellowstone National Park. You might think of its geysers like Old Faithful, its roaming bison herds, or its colorful hot springs. These features capture tourist imaginations still today, but for thousands of years, various indigenous nations, including the Shoshone, the Crow, and the Lakota, saw Yellowstone as sacred ground. In their oral traditions, the heat, geysers, and bubbling ground were signs of Earth's living spirit, meaning forces beneath the surface that needed to be respected. Today, scientists describe Yellowstone as a hotspot volcano system powered by a mantle plume. While the cultural explanation speaks of Earth's breath and spirit, the scientific explanation speaks of convection, molten rock, and mantle heat. These are two different ways of explaining the same extraordinary phenomenon. So, one question we want to explore today is, what lies beneath Earth's surface? And how do scientists investigate the 3,960 miles to Earth's core if they cannot dig down and see it directly? So here's the problem. Humans simply cannot dig very far into Earth. The deepest mines on Earth are a little over 3 kilometers deep, which is about 2 miles. To put that into perspective, the distance to Earth's center is about 6,370 kilometers. That is like comparing a jog around a soccer field 10 times to running the same field 21,000 times. Clearly, digging our way to Earth's center is impossible. So, how do we know what's down there? Scientists look for indirect clues. They watch, for example, how earthquakes shake the Earth. They analyze lava and volcanic gases that bubble up. And they recreate Earth's extreme conditions in labs. This type of detective work, piercing through evidence from multiple sources, lets us build a picture of Earth's layers, much like the indigenous peoples of Yellowstone built explanations of geothermal power from what they were able to observe around them. Both use patterns of evidence, one through oral tradition and one through seismic waves and experiments. So let's break down the scientific detective tools. First up, seismic waves. When an earthquake happens, it sends out waves that travel through the Earth. Some waves speed up, some slow down, and some even disappear. By studying these different changes, scientists map the hidden layers. Think of it like an ultrasound or X-ray for the planet. Secondly, volcanic clues. Lava and ash bring material from deep underground. By analyzing what minerals are inside this lava or ash, scientists infer the temperature, pressure, and chemistry of the mantle below. Thirdly, lab experiments. Scientists crush and heat rock samples to simulate pressures and temperatures deep inside Earth. This shows how rocks change, whether they melt, flow, or transform into new minerals. This is like piecing together a puzzle where no one piece is enough on its own. We like to compare it to a story of the blind man and the elephant. It's the blind men and the elephant. Each blind person touches a different part, but only by combining their perspectives do they understand the whole. Scientists, too, need many perspectives to understand the Earth. The crust is Earth's outermost skin, but less than 1% of Earth's mass. Think of the skin on an apple compared to the fruit inside. That's the crust compared to the mantle and the core together. Of the crust, we have two types. Continental crust, which is somewhere between 30 and 100 kilometers thick. It tends to be less dense. It tends to be rich in silica, aluminum, and potassium. Continental crust is thickest under mountain ranges where it wrinkles like skin under pressure. The second type of crust is oceanic crust, which tends to be somewhere between 5 and 10 kilometers thick. It tends to be denser, as well as being rich in iron and magnesium. And this oceanic crust is constantly recycled at mid-ocean ridges. So, we can ask a question. Why do continents ride higher than oceans? First, continental crust is less dense, so it floats on top of the mantle like wood floats on water. Secondly, oceanic crust, being denser than continental crust, sinks lower. The result, meaning putting these things together, continents stand above sea level, while oceans form deep basins. This difference in density is why Yellowstone, sitting on continental crust, stands high above sea level. Indigenous stories about the high land that breathes fire and water fit perfectly with the geological reality of a continent riding high on mantle heat. The mantle makes up about 67% of Earth's mass and is about 2,900 kilometers thick. Although it's solid rock, the high temperature and pressure make it capable of flowing, but very slowly. Imagine honey that takes years to ooze about an inch. That's mantle flow. Now, check this out. Mantle rock flows at about the rate that your fingernails grow, which is measured in centimeters per year. This mantle movement is what drives plate tectonics, and in special places like Yellowstone, hot columns of mantle rock called plumes rise directly toward the surface, creating geysers, hot springs, and even super volcanoes. Convection, which we've talked about in the past, is the heartbeat of Earth's interior. Let's consider the following sources. First, consider a heat source. Energy left over from Earth's formation plus radioactive decay in rocks heats the bottom of the mantle. Second, hot rock rises because heat causes rock to expand and become less dense. Once it is less dense, it moves upward. Next, we have cooling and sinking. Once away from the heat source, because the hot rock has risen, that rock cools. Because it cools, it then contracts, meaning it becomes denser and then begins to sink back down. And lastly, the cycle continues, meaning this loop repeats endlessly, which drives the movement of tectonic plates. Now, students often think all mantle is molten liquid. It's not. It's solid rock behaving plastically under high temperature and pressure. The Crow Nation described Yellowstone's geothermal activity as Earth's breath rising from below. But notice the similarity. Science calls it convection, and indigenous tradition calls it breath. Both describe constant motion beneath the land. Scientists map the mantle using seismic tomography, just like doctors use CT scans. What we'll notice is that warm material slows down those waves. Cold material speeds them up. And thousands of earthquake readings combine into 3D modeling. These images, once combined, show mantle plumes like the one under Yellowstone. The indigenous story is that Yellowstone is alive and breathing, and seismic tomography literally confirms that there is movement and heat beneath the park. The core is Earth's metallic center. It's roughly 1/3 of its mass, about 6,856 kilometers across. But there are two zones. There's the outer core. It's liquid iron and nickel. It ranges somewhere between 4,000 to 6,000 degrees Celsius. And it, the outer core, the liquid iron and nickel part, generates Earth's magnetic field through convection. But there's also the inner core, which is a solid iron and nickel ball. Solid iron and nickel. The inner core is hotter than the surface of the sun, but it is kept solid because of the crushing pressure it experiences. This geodynamo explains Earth's magnetic field, which indigenous peoples used for navigation long before compasses. They would observe stars, animals, and natural cues. So here's how we discovered the outer core is liquid. First, earthquakes produce two main seismic waves. There are more, but these are just the two main types: P waves and S waves. Secondly, P waves travel through both solids and liquids. Number three, S waves, on the other hand, travel only through solids. 4. Scientists noticed S waves vanish in certain areas on Earth. We call this the shadow zone. And so our conclusion is that those waves hit a liquid layer, which we now know as the outer core. This was one of the greatest scientific detective stories ever told, using evidence from earthquakes to quote-unquote see what we could never touch. Now, to grasp Earth's scale, let's consider the following proportions. The crust makes up less than 1% of Earth's mass. The mantle is roughly 67% of Earth's mass, leaving around 32 to 33% of Earth's mass to the core. Now that core is roughly 6,850 kilometers across. This means the familiar land that we live on, which is the crust, is just a thin film above an enormous moving system. So let's trace the layers one by one. First, the crust, somewhere between 0 and 100 kilometers down. This is made of brittle rock where life exists. Next down, the upper mantle, somewhere between 100 and 660 kilometers. This is the flowing asthenosphere, which drives plate tectonics. Going down still further, the lower mantle, somewhere between 660 and 2,900 kilometers down. Here we see hot rock under extreme pressure, and heat is transferred through plumes. Going further down still, the outer core, somewhere between 2,900 and 5,150 kilometers down, we see the iron and nickel core in its liquid state. And this is the area of Earth's core, the outer core, that generates Earth's magnetic field. And lastly, we come to the inner core, somewhere between 5,150 and 6,370 kilometers down. This inner core is a solid ball of iron and nickel, hotter than the surface of the sun and held in the solid state by extreme pressure. So this journey from Yellowstone's surface to the core ties cultural traditions of a breathing Earth to the scientific layers beneath the story. Earth's interior is not frozen in time, however. It's dynamic, constantly changing. Mantle convection drives tectonic plates. It creates volcanoes and shakes the crust with earthquakes. But why does this matter? Predicting volcanic eruptions, like Yellowstone's potential activity, locating valuable minerals and geothermal resources, as well as understanding Earth, helps us model other planets. And in closing, we know that indigenous nations already saw Yellowstone as living, dynamic, and sacred. Modern science, through seismic waves and convection models, say the same thing, but in different words. Earth's interior is truly alive, and it shapes everything on its surface. At this point, you should be able to generate a full and appropriate explanation or response to today's essential question. How do physical conditions and mineral composition change with depth beneath Earth's surface?